All right, so morning everyone. Brief intro for me. I actually started my career journey as an electrical engineer, doing industrial automation, which included building data centers and installing the electrical equipment into them. Nowadays, I'm an SRE. So instead of building the data centers, I just run software in them. To be honest, that's a lot easier of a job. I can do it from a comfy office chair and air conditioned rather than walking down around a factory floor in a hard hat and steel cap boots. So that's better. As Matt said, I'm currently at Google in Sydney. And for the last 3 years, I have been working on Google Cloud Firestore, which is our cloud NoSQL database offering. Of course, if you find any of this stuff interesting, I'm always happy to talk more about it. You can come find me afterwards. We can chat over lunch, whatever you like. OK, so let's start with some definitions. Capacity. Capacity is provisioning enough resources to handle your incoming request load. Resources, in this case, we're talking about servers, disk, SSD, that sort of stuff. And the request load can be internal or can be external. Efficiency, that means minimizing the total cost of our system. So running it as cheap as we can. Why do we have versus? What's the versus? Well, generally, these things are at odds with one another, right? You can make your system much cheaper by provisioning less resources. But if you provision less resources, that gives you less ability to handle incoming changes in incoming requests. So there's a bit of tension here. Let's talk about how we can make trade-offs between the two and maybe some ways that we can optimize for both. So this talk is a collection of tips and lessons that we've learned from building Cloud Firestore. Brief description here. Google Cloud Firestore is a fully scalable NoSQL database where you only pay for what you use. So let's dive into the ramifications of what that actually means. Fully scalable. So we have no quotas. That means our customers can ramp their traffic up and down at any point in time without reserving that quota, reserving that capacity ahead of time or telling us about it. And that means that we need to be able to handle any amount of traffic coming in at any point in time. So it generally means we need to have some level of idle capacity ready and waiting for new requests to come in. Pay for use. So when you use Firestore, you only pay per request. So you pay if you do a get, you pay if you do a commit or a delete. This is different to typical VM provisioning where you pay to have a server and you have that server running for you, long term, you're paying over time. Here you only pay at the point where you use it. That means that the customers are not paying for the resource usage over time. We are paying for it, which means that we have idle servers sitting there running, waiting for load to come in. We're paying for that, and we are that means we are interested in increasing the efficiency of those servers and running less of them. So if you are running a service that has variable workloads where you don't know exactly how much load you're going to have ahead of time, and you're paying for your own resources, then these lessons will probably apply to you too. All right, let's start by talking about capacity. How do we make sure that we are correctly provisioned? So this is not a talk about how to turn on autoscaling for your service. In fact, we are going to assume that you already have an autoscaling foundation. If you don't have that, do that first. That will be the single biggest win that you can get in this space. It's going to improve your reliability because it means your system will automatically adjust to changes in load. And it's going to be a toil win because you're not going to have some engineer sitting there going, all right, scale servers up, scale servers down, flicking buttons. Nobody wants to do that. When we talk about autoscaling, usually we're talking about horizontal autoscaling, so increasing your replica count, spinning up new servers to handle an increase in load. This is typically available on every hosting platform. It works in most cases. Some cases it doesn't work so well. So for example, maybe you have like a stateful service or like a leader elected service or something like that. In those cases, you might want to consider vertical autoscaling. Vertical here being adding more CPU and RAM to your servers in place, so making bigger, fatter servers rather than more of them. The downside is that vertical autoscaling is not necessarily available everywhere. It depends on which platform you're running on, but I do know, for example, that it is available on Kubernetes. So you've got autoscaling set up. You need to make sure you choose the right signal. Most commonly, this metric will be CPU utilization or memory usage, but you can scale based on other signals as well. So for example, you might scale on active thread count or the number of active requests that are in flight on your servers. It's important that you align all of your bottlenecks with this scaling signal. And if you can't do that, you need to over-provision them. Because if you don't, and you have multiple bottlenecks that are not aligned with your scaling signal, you can end up stuck and overloaded on those bottlenecks, and the system won't scale you up because it thinks that you're healthy. For example, if you cap out on thread count, but you have a low CPU utilization, and that's your scaling signal, your system's going to be like, nah, we don't need to add more servers with more threads. You're good. And it won't scale you up. So you end up stuck and overloaded in that case. So make sure you always align them. For that example, in Firestore, what we've done is we have removed that bottleneck by converting most of our services from a synchronous model to an asynchronous model. So removing those bottlenecks is always the best thing you can do. Let's take a look at some of the common load patterns that you might encounter. So starting from the top left, we have flat. This is like the trivial case, really. You don't need to do any scaling because your traffic's always going to be the same. Moving on, diurnal. That's quite common. Typically, this oscillation, we'll see it as like a daily cycle or sometimes like a weekly cycle. This one's quite easy to handle because you generally know what the maximum and the minimum are going to be based on past history. And the scaling, it scales up quite slowly, right? A couple of hours that starts picking up. And it gives your auto-scaling system time to respond to that and scale up. Next along, a slow ramp up. This is what a well-behaved workload will look like. So something that ramps up, but does it fairly slowly with enough time for your auto-scaling system to pick up the slack. Moving down onto the next row, we're getting a bit harder. Traffic spike. So you might see this if you've launched a new product or feature, or your website has just gone viral, and suddenly everyone's rushing to it. Right? This is hard because you don't know how big that spike's going to be. You don't know what the maximum is going to be. And you don't know how fast it's going to be. It can be really fast, and it might not give you time to react and provision enough extra capacity to handle that load. And lastly, we have our bulk workload. So this is typically some automated system has turned on, maybe it's like a cron job or something, and it's just suddenly hitting you with a whole load of traffic all at once. This is the hardest because you've got that vertical cliff there, right? You don't have any time to scale up, right? You need to either be provisioned initially or you're going to be overloaded. So you can see that the ramp-up speed is really important, right? The slower the ramp-up, the easier it is to handle and the more time your auto-scaling system has to react. So wherever possible, you want to control that ramp-up speed, right? This is easier if you're talking about an internal service and you control the client, but it can be done if your clients are external as well. So for example, maybe you publish SDKs, and in which case you can build throttling and rate limiting into your SDKs. Or in Firestore's case, what we've done is we've published a best practices guide online, and we have something we call the 555 rule, which is you can start with 500 requests per minute, and then every 5 minutes you can scale up by 50%. And this gives our customers a good idea of like how fast can I scale before I run into performance problems. What's a good speed to do that? So if you want to handle spikes, yes, you could over-provision. You could spin up a whole load of servers and have them there ready and waiting. But over-provisioning is really just kicking the can down the road. Eventually, you're going to have a spike that's too large to handle. So we've talked about, auto-scaling is not instantaneous. Ideally, we should be provisioning just enough headroom to handle that spike while we give our autoscaling system time to scale up. The amount of headroom that we need is going to depend on how big are the spikes that we're expecting and how fast can our autoscaling respond to that. How fast can we scale up? It's also affected by the homogeneity of your customer base. If you have usage that is spread out over many smaller customers, then it's less likely that all of those customers will spike their traffic at the same time. Right? This is a classic example of the sum of peaks being less than the peak of sums. Sorry, other way around. Peak of sums less than the sum of peaks. On the other hand, if your usage is dominated by a couple of users, and they each have a relatively large share of it, then a change in any one of your customers can represent a large change in the overall capacity of your system. And in that case, you might need more headroom. So at this point, we can start our efficiency formula, which I've got down the bottom there, which, the efficiency of our system is 100%, but then minus the headroom that we have to provision for the expected traffic spikes. And so we can say this is the maximum size of an expected traffic spike. Another capacity risk that you may have to deal with is stockouts. So at the end of the day, cloud resources, they're really just machines running in a data center somewhere. It doesn't happen often, but they can run out. This is particularly true given the current global silicon chip shortages. These machines are harder to acquire nowadays. So in a stockout case where there's no capacity left in that data center, you're not going to be able to scale anymore. So if you have an increase in traffic and you're stuck in that data center, you're going to be overloaded. So we mitigate this by using more zones, more availability zones, and more regions. Right? You want to spread your footprint out as wide as you can. This gives you access to more resources, and it reduces the likelihood of being stocked out. Right? One data center, one availability zone might stock out, probably not all of them at the same time. It's also a cost-saving measure because it gives you access to more spot instances. Right? Typically, these are the first things that stock out. So if you're spread out, you can generally access these more freely. You want to build capacity agility. So your load and your footprint should be able to freely flow between different availability zones and different regions. So that way, if one of them stocks out, you'll automatically scale up in the other ones without having to touch anything. Usually, you can achieve this with a cross-zone auto-scaling group. And if your hosting provider adds new zones, take advantage of them as soon as you can. Since we're talking about zones, let's talk about failover. Right? As SREs, we love redundancy, and you want to protect yourself against any one zone going down. Shown here, there's two common examples of how to do failover. On the left, we have an active-passive model. So you have one zone that is your active zone, and 100% of your load is going to that zone. And you have a second zone that's kind of sitting there doing nothing, waiting. And if you have something go wrong with your primary zone, then all the load shifts over, and that passive zone now becomes your new active zone. Another model is the N+1 model. So you're using a certain number of availability zones with one extra. And the load is equally spread out across all of your different zones. And all of them are slightly over-provisioned, such that if one goes down and that load then shifts back into the other zones, they're all now going to be at 100% capacity. Now, I say N+1 here, but you can do N+2, N+3, whatever your reliability needs are. Once you've got your failover provisioning set up, you need to test it, right? Because you may think you're correctly provisioned, but some of these things are really hard to estimate. For example, maybe only some of your traffic fails over. Maybe when you do a failover, you have cold caches and you have worse performance for a short while until things get up and running. Or maybe you discover new bottlenecks like network that you didn't know about until the failover scenario. So make sure you're testing. There are tools available to do this, and if your toolset supports it, try and do these failover tests actively. Try and incorporate them into your load balancing so that they're continually being tested and that they're not a separate manual process that you test once a year or once a month. Okay, so you're now correctly provisioned for your incoming capacity, but how do we do that cost effectively? How do we do that cheaply? All right, we're in a recession right now. We want to save money. Let's start by tuning our autoscaling. So the default autoscaling policy you get is usually pretty good, but often you can tweak some other parameters, you can feed it your own metrics, and you can make it a little bit more efficient. Here's some parameters to consider. Firstly, your autoscaling targets. What proportion of your incoming load do you actually want to target? Do you want to target the max load, so the P100, or something else? Consider this example where you have highly volatile, spiky load. Right? You could target the maximum of this load and use that top line there. But then most of the time, you don't need that capacity. So that gap between the dotted line and the blue line, that's wasted capacity. So maybe you want to reduce your target. Maybe you want to target the P99 or the P95. And that can bring your capacity provisioning down much lower. You can save a lot of money there at the cost of being slightly overloaded during that spike period. So you need to consider, for your load, how volatile is it, how spiky is it, and what target do you want to set for your autoscaling? Because max is not necessarily the best thing for you. Your window length, the reaction window. So this is basically how fast your autoscaling system responds to the incoming changes in traffic. If you have a short window, that's generally good because it makes you more responsive. You can scale up quicker. The flip side is that sometimes you overshoot. And if you have short spikes, maybe that spike will have disappeared by the time you scaled up. And so that scaling was not very helpful. On the other side, if you make it a long window, then you'll make sure that you only scale up for sustained load. Another factor is your stabilization or decay period. So a long decay period means that you will be prepared for subsequent spikes. Maybe there's another spike coming in 10 minutes time or an hour's time, and you've now got the capacity ready to handle that. But the downside is that you can see that big area there. That's a big area of resource inefficiency. If you have a short decay period, that means that you track the load more closely, so you'll scale down quicker, save some money, be more efficient. But it also means that you'll have higher churn on your servers, right? You're going to be scaling up and down more frequently. Your servers are going to be starting and stopping more frequently. So you need to make sure that there's no negative effects when that happens, right? If customer requests are in flight on your servers and your autoscaling system decides that it's going to scale down all the time, you need to make sure that that's okay. And of course, if you put this decay period too short, then you can get oscillations, right? It might go up and down constantly, even if your load is relatively flat. So we can do even better here by using dual windowing. So we have a short window and a short stabilization period, and that will account for our short-lived spikes that appear and disappear. And then we have a separate window and a longer stabilization period, and we use that to hold on to resources that we need in the steady state. And the signal that we feed to our autoscaling system is the max of the two of them. So that way we go up and down for a short spike, but for steady state traffic, we hold on to a lower amount. Lastly, the faster your startup time of your servers, the quicker you're going to be able to respond to changes in traffic, the quicker you're going to be able to scale up. So startup time is important. Keep that low. Let's talk about load balancing. So a common failure mode of load balancing, or more like poor load balancing as seen here, is you get a high spread of utilization between your servers. So some servers are really heavily loaded and some servers are not very heavily loaded at all. We get performance degradation when any one of our servers is overloaded. And that means that we need to provision our resources such that none of our servers are overloaded. Consider these two examples. Right? On the left, we have good load balancing. So the difference between the most heavily loaded server and the least loaded server is not that high. And then on the right-hand side, we've got poor load balancing, where there's a huge disparity between the servers. Both of these cases have the same total amount of load, which means that their mean load is the same. But on the right-hand side, you can see that the maximum load for a server is much, much higher. Okay? And this maximum, that's the amount that we need to provision for to make sure that nothing's overloaded. So that gap between the max and the mean, that is inefficiency. And the closer you can pull those two together, so the better your load balancing can be, the more efficient your service is going to be. So this is another factor in our formula. We can add it down at the bottom. Our efficiency is now, we also have to provision headroom to account for this load imbalance. Now I'm going to change the formula slightly. Your traffic patterns, they're going to vary over time, and so will your load imbalance, which means that both of these things can be modeled as a probability distribution. The chance of encountering the worst case traffic spike and the worst case load balancing at the same time, that's probably quite unlikely. So what we're actually interested in is the combined probability distribution of both of these factors. So I've denoted that there as P, and what we want to measure against is the maximum of this combined distribution. And this max should be lower than the individual maxes of each of these factors added together. Again, we've got peak of sums being lower than the sum of peaks. So we talked about how to make sure that we have capacity for a failover. How do we do that cheaply? If you're using the n+1 model, the best thing you can do is increase your n. So the +1 in the n+1, that's your inefficiency. That's the resources that are sitting there idle doing nothing. You know, how often do you have a failover? Probably not very often, like once or twice a year, maybe. So that means the rest of the year, you're paying for those resources and they're doing nothing for you. If you make the n bigger, that +1 becomes a smaller fraction of your overall load. As an example here, if your n is 1, so you're running it with 2 zones, then the +1, that's 50% of your resources. You're running at a 50% efficiency loss for redundancy. If you make that n bigger, so now move to 5 zones, that +1 is now only 20% of your resources. So you've gained a massive amount of efficiency just by using more availability zones and changing no other properties of your system. Of course, there is a caveat to that. If you have a high number of fixed costs per zone, then you don't want to have too many zones, because then you end up being mostly fixed costs. So the optimum can be somewhere in the middle. If you are using an active-passive failover model, consider using instances for your passive zone. Consider using instances that have a lower SLO, like spot instances. Or you can consider under-provisioning that secondary zone and relying on autoscaling to cover the extra gap. As you fail over, you autoscale up for that remaining amount. Consider these factors. How fast does your failover happen? It's probably not instantaneously. In the event of a network partition, does 100% of your load fail over, or only some? And think about your error budget. Can you afford to be overloaded for some number of minutes during a failover while you rely on your autoscaling system to scale you up? So for your secondary zone, maybe you want to target something like 70 or 80% capacity instead of 100%. So this makes it the third factor in our efficiency formula. We now need to budget for this failover capacity as well. Batch traffic. So here we are defining batch traffic as anything that isn't directly user-facing or traffic that is latency tolerant. And the latency tolerance part is key, because that allows us to be more efficient with this traffic. And how we do that is we take the traffic and we split it out. So we run it against a different set of servers. And those servers, we can use a lower SLO. So maybe we want to run them on spot instances or something like that. And we can run them hotter. So we can target a higher utilization in our autoscaling setup for these servers. What that looks like is, for example, moving from that green line down to the dotted line for our batch traffic. What that means is that, yes, probably they will be overloaded more often. And they'll have worse performance. But that's OK, because we've established that this is latency tolerant. And so the lower the SLO you have on a particular class of traffic, the more efficient you can be with that traffic. VMs come in many shapes and sizes. Most commonly, you're going to be having to choose your CPU and your RAM. If you pick the wrong shape, then that means that you are paying for resources that you are not using. So how do we find the right shape? You need to test your service. Test it with varying amounts of load and plot a line showing what the relationship is between your CPU usage and your memory usage as you increase load on your server. Then plot that line against the shapes you have available to you and pick the closest one. If you have to make a choice, prefer over-provisioning on memory instead of CPU. If you run out of CPU, your service is probably going to get slow. You might throw a few errors. But if you run out of memory, things tend to crash. And that's usually a worse outcome. We heard from Brendan yesterday that the number of cores per machine has been increasing significantly in the last 10 years. This gives us more flexibility in sizing our VMs because we can now make them much bigger. So this image here has actually already been published a year or two ago by Google online via O'Reilly. You can find the article about it. But basically, it shows the gain you get when you move to a bigger server. So here we're comparing 2 smaller servers versus 1 double-size server. And when you move to a bigger server, your fixed costs stay the same. Right? So you're only paying that cost once instead of twice. So that represents some savings. Your variable costs, they double, because that represents the incoming load that you're getting from your traffic. That stays the same, so no savings there. And then the headroom. The headroom, you save a little bit there as well, because again, peak of sums versus sum of peaks, you don't need quite double when you add them together. Another benefit of moving to less bigger servers is that less instances means you have less load balancing spread statistically. If you're interested in that topic, my colleague Julius Plenz actually gave a whole talk on it back in SREcon in 2019, and the recording is available online. Of course, there is a limit to how big you can go. If you get down to too few instances, that's probably starting to become a reliability risk. So if you have just 2 instances, that's probably too few. You also get less smoothness in your autoscaling. So for example, if you autoscale from 4 to 5 instances, that's a 20% capacity step change. Versus if going from 100 to 101 servers, that's much smoother. So getting down to low server numbers, you can get some bumpiness with your capacity graph. And of course, if you get too big, you'll start hitting other bottlenecks, like you might run into more lock contention. You might start getting bottlenecked on the number of open sockets you can have on a machine, stuff like that. So make your servers as big as you reasonably can, but no bigger. You can make resource trade-offs to optimize for cost. So we know that SSDs are more expensive than hard drives, but in terms of IOs per dollar, they're actually cheaper. So if you're running a heavily IO-bound operation, it might be a cost reduction to move from hard drives to SSDs, and even more so if we're talking about RAM. If you have a variety of data access patterns, consider splitting it up between all 3. So the heavily IO-bound stuff, put it on RAM or SSD. The stuff that doesn't get accessed very frequently, put that on disk. And if you want persistence, then you can use stuff as caches, right? You can use RAM as a cache, so all the IO hits the RAM, and then the actual persisted data sits on disk. You can also make this trade-off with CPU and RAM if you're using a garbage collected language like Java. Right? If you use a lower heap, a smaller heap, you'll use less memory at the cost of you'll be spending more CPU cycles more frequently doing garbage collection. And if you provision a bigger heap, you'll do less garbage collection, less CPU utilization. So you can trade one off against the other there. The sweet spot for all of these is going to depend on the hosting platform you're on and the pricing of the different resources. Okay, lastly, let's talk about overload and a couple of strategies to handle that. So overload is going to happen eventually. Of course, we want to be able to handle overload. But why specifically do we want to handle overload for the purposes of efficiency? In an auto-scaled system, our goal is to handle the overload until we can scale up. And our ability to do that determines how far above the capacity line we can go. So for example, in this diagram, if we can't tolerate any overload, then we are that green line at the top. That's how much headroom we need. If we can tolerate overload, we are that dotted line. We can bring our headroom down and save. So the better you can handle that overload, the more efficient you're going to be. And in fact, you should aim to keep your headroom consistently low so that you're consistently testing your overload defenses, right? You want to know that these are always active, always working, rather than waiting for an overload scenario to come along down the road and suddenly being surprised that you have some cascading failure scenario and that everything falls over. So how much overload can we handle? We need to understand our limits. This is a graph from performance testing of one of our services. It measures the CPU utilization against the successful throughput of the system as we ramp up the load. And you can see that performance is not linearly correlated with utilization. At the low end, we are dominated by our fixed costs, and we are highly inefficient. And then as the load goes up, more of that utilization represents real work being done. Our caches get more efficient, and our overall efficiency gets better. But at the top end, we start running into bottlenecks, right? Lock contention, memory pressure, we start spending time doing work on requests that end up timing out and deadlining and throwing errors. So these will manifest as performance issues, latency and errors. So we need to know what our upper limit is, right? Our peak efficiency is not 100%, it's actually this limit here. So this is what I've denoted as a safe CPU, and our efficiency formula changes, right? This is now our maximum possible efficiency. You need to do these types of load tests frequently, right? Because this curve will change over time as you add features, as you rework your code. And so you need to be on top of it and see what it's constantly doing. So load shedding, this is one strategy for handling overload more effectively. Load shedding is when we intentionally return errors when we are overloaded. And we do this because rejecting one request and successfully serving another one is better than trying to serve both requests at once and then timing out, deadlining them, and both of them end up being errors anyway. So to be successful at load shedding, we need to be rejecting fast and we need to be rejecting early. So very early on in the request lifecycle, that's when we need to recognize that we're overloaded and reject those requests. This works best if you've got cooperation from both the client and the server. So the server sends errors when it's overloaded, and the client recognizes either errors or latency and then throttles itself and does exponential backoff. But it can work if you just have one of those in place, if you control just the client or just the server. With load shedding, we can also distinguish between retryable and non-retryable errors. Right? So our load shedding client can try a server, and it might come back and say, no, sorry, I'm overloaded. And then we can try a different server, because maybe he's got capacity. And this is actually good because it helps us shift load away from our heavily loaded servers and towards our underloaded servers, right? So it actually gives us better load balancing. It brings our spread between the most heavily loaded and least heavily loaded servers closer together. And as we saw before, that itself is an efficiency gain. And then, of course, if you try a couple of servers, you're overloaded, you're overloaded, you're overloaded, well, probably at that point your whole system is overloaded. You're not going to be able to successfully handle this request with the resources you have available to you right now. And at that point, we should just return an error back to the user. QoS, that's another technique. So this is a term that is borrowed from networking. We classify our requests into different priorities, and we propagate those priorities all the way down the stack. So a request that comes in as high priority is treated as high priority by everything in your stack. When you get overloaded, you start at the bottom and you start discarding requests. And you work, as you get more overloaded, you start working your way up. This means that you're always protecting that high priority traffic. An even better thing to do here is partial degradation. So if you can change how you're handling your requests to do less work, or to serve approximate values, or to turn off some of your expensive functions, then you should do that as well. And that will decrease the load you have on your whole system while you scale up. Lastly, fairness. So fairness is quite a desirable property, right? We want to give as many of our customers as good of an experience as we can. If a single user is overloading the service, we don't want that to affect all of the other users of our system as well. So we want some kind of isolation guarantees between the users of our system. So think about overload scenarios when you're picking your scheduler, because your scheduler is often going to be what determines how you divide out your resources and who gets how much time on your servers. In Firestore, we use a stride scheduler, and that attempts to allocate an equal number of CPU seconds of work to each of our customers. So we're not divvying up work per request, we're doing it per customer. And when you're doing your load shedding, you might want to first consider dropping the traffic of the user that is overloading your system before moving on to dropping the traffic of other users of the system as well, right? We don't want to necessarily negatively impact those other users if they're not doing anything wrong. So far, our efficiency formula has been budgeting for the maximum possible load, right? That's that P max there. If you want to avoid any overload at all, then that's what you need to budget for, the maximum. But it's also very expensive, right? You can see the distribution there. Often your load distribution will have a very long, thin tail. So what if we can handle some overload? Right, we've just talked about some ways of mitigating the impact of overload. What should we target instead? Well, the error budget provides a useful tool for thinking about this. Right? If you have an SLO of 99%, you can afford to be overloaded 1% of the time. And so therefore, you set your headroom target to the 99th percentile of the load. And then 99% of the time, you've got enough capacity to handle your load. 1% of the time, you're overloaded, and you eat that into your error budget. Of course, overload isn't the only thing that can burn your error budget, so maybe you only want to allocate a fraction of your budget to handle overload. But the concept is the same. Right? And the stronger your ability to handle overload, the lower you can bring that percentile target. Right? It's a very small tail, and so you don't need to bring the percentile that much lower in order to get a lot of savings and really bring your headroom down. So what are our takeaways here? Efficiency is primarily determined by this formula. Reducing the impact of any one of these factors is going to give you an efficiency boost, right? So the maximum utilization that your servers can run at, how large your expected traffic spikes are, how bad the load balancing is, or how good the load balancing is of your system, and how much capacity you're provisioning for failover. Beyond that, you want to autoscale everything, absolutely everything. Some things are harder than others, but I can guarantee you almost everything can be autoscaled. Expand your footprint to minimize your N+1 overheads. Use as many regions, as many availability zones, as many data centers as you can. Test your failovers regularly to make sure that they are doing what you think they are going to do. Understand what resources you actually need, and then pick the right configuration of resources to match that. Right? Sometimes you can trade off one resource type versus another to find a price optimum. And lastly, being more reliable under overload improves your efficiency because it allows you to bring that headroom down. Okay, that's all I have for you. The Slack channel is open for your questions listed there. Thank you very much.